This is problem 20-21. The uniform slender rod AB with a weight of 3 pounds and a length of 2 feet is resting on a frictionless horizontal surface when it is struck with an impulse of P times delta T equal to 2 pound-seconds as shown in the figure. Okay, so let's look at that figure real quick and I'll continue reading the problem. So we've got the rod supported by a pin, supported by a wall. Okay, it's a frictionless pin. The length is equal to 2 feet, and there is going to be a center of gravity, and there's going to be an impulse. All right, so let's keep reading the problem. If the duration of the impact is delta t equal to 0.002 seconds, determine the distance b for which the average force exerted on the rod by the frictionless pin at A is 0. So they're wanting us to figure out how we can have an impulse that basically cancels out the vertical forces. So it says that the average force exerted on the rod by the frictionless pin at A is 0. So the impulse, and this is tricky, the impulse is pushing on the rod in a way that the rod moving, I'll draw on the diagram, the rod moving upward, actually let me put it here, upward, and also rotating will balance out so that this pin doesn't have to do all of the work to keep the rod from not moving. I hope that makes sense. This takes some imagination. I know even if we were in class talking about this, I wouldn't necessarily be able to confirm if you're thinking about this correctly. So discuss with each other about what this idea means, where the average force exerted on the rod by the frictionless pin at A is 0. It's kind of like the impulse and the rotational inertia and the linear inertia all kind of balance out during that period of time, that the pin basically doesn't have to support the rod, but only during that moment. Okay, so that is a tricky question to understand what it is they're asking for in the first place. So let's go ahead and look at the math, and hopefully the math will help clear up any confusion and ambiguity of understanding here. So first, let's go ahead and just calculate some properties of this rod. So we're going to have a support reaction AX and a support reaction AY, and we're going to have a P of 2, this is the impulse value, it's going to be 2 pound-seconds. Okay, so what we're trying to find is actually this distance B. Where does that 2 pound-seconds impulse need to be in order for all of this to balance out? All right, first let's calculate the rotational inertia of the rod. So rotational inertia is equal to, of a slender rod is 1/3 the mass. So 3 pounds divided by the acceleration due to gravity, and then times the length squared. So 2 feet squared. All right, that calculates out to be 0.124 slug feet squared. All right, and then what we want is we want to know how fast is this center of gravity going to move based on its rotation, because that G can only rotate up or down because of the fixed pin over here. All right, so we can do a relative acceleration equation. So the velocity of G is equal to the velocity of A, which isn't moving, these are vectors, plus the velocity of G relative to A. All right, well, we're finding the velocity of G. So velocity of A is 0, and then it's going to be plus the distance G is from A, which is 1 foot, times the angular velocity of the rod. And this is a J hat vector. So G will, from that position, G will not move in the X direction, positive or negatively. G can only move exactly downward or exactly upward when in this position, this exact moment. So therefore, if the rod moves even slightly off of that, then there will be an I hat component. But in this exact moment, when the rod is perfectly horizontal, is a J hat only. Okay, So that means we have a velocity of g value. So the velocity of g is equal to 1 omega, only downward, all right? So this is actually the velocity of gy. I'm going to imply the j hat by labeling this gy. Now we can go to the linear momentum equation. So we know that the rod has no initial momentum, but this is the rod at point G. We want G's linear momentum. Okay, so there will be no initial momentum, and then we're given the impulse. There is going to be 2. Sorry, that shouldn't be equal sign because the impulse is on the other side of the equal. That should be a plus. All right, and then equal to the final momentum, which is going to be the mass times the velocity of gy, which we know is 1 omega. All right, so now we can actually solve for omega because we have 2 equations, 2 unknowns. So omega final is equal to 21.47 radians per second. All right, well, what do we do with this? Well, then we can use the angular momentum principle and we can calculate B because we know omega. So the angular momentum is 0 at first, and then there is a torque, an impulse that is 2 times the distance. All right, so we don't need to know the time. We already know what's going on here. We already got the impulse. And then we have the rotational inertia that we calculated, so 0.124 slug feet squared times omega. And we already know the value of omega, so B is the only unknown. So B is equal to 1.33 feet.